Okay. So these are the projects which you can work on. These are just suggestions, and they're taken literally from the 2 years ago. I haven't changed anything because I was not prepared to do that. So here are, this is my generation, 96, more or less. It's not even my generation. So these are, when you go from 1D to 2D, right, in the spin chain, there's a surprise somehow. That was the title of this paper of D'Agotto and Morris Rice, is that if you take a chain, you have no spin gap. If you take a ladder, you have a spin gap. If you take 3 chains, you have no spin gap, etc. There's those odd even effects, which we know now are related to topology, the onset of a Wessumino-Witten or theta term or not, right? So it's a rather interesting piece of physics, and you can check this, right? So the idea would be to take the Hubbard model on the n-leg ladder and take ladder one, no spin gap. How do you calculate a spin gap? You would calculate the spin-spin correlation functions and see if they decay with a power law or if they decay exponentially, okay? So that's just running the code and verifying those a classic, right, if you want.
Does it also show up in Max?
Yes, it will also show up in Maxent. So you can do that in Maxent. You could do the spin. Yeah, that would be, especially if you take a T perp, which is very big for the 2-leg ladder. So they would show up in Maxent, and you will see basically if the T perp is not so big, you will see basically a gap and then the 2 spin-on continuum on top of it. So it's a rather nice thing to do, right? I mean, these are all nice subjects, in my opinion. Then there is the Heisenberg model. The Heisenberg model actually has, so you all know the Heisenberg model, right? Now, the Heisenberg model, we know that it has a higher symmetry than SO3. It has an SO4 symmetry. And this SO4 symmetry tells you that if you measure the dimer-dimer correlations, or if you measure the spin-spin correlations, they get both a 1 over R decay. But there are some logarithmic corrections because there's one parameter which is marginally irrelevant, right? Right. So that is something which is surprising and which tells you that the Heisenberg model, the one we know, is basically comes from a Wessumino-Witten Lagrangian, an O4 Wessumino-Witten Lagrangian with basically so this would be this Lagrangian. We don't need that, but it's but this Lagrangian, when you think about it, why is it interesting? It's interesting because this is the first thing which people thought about when they're thinking of DQCP, right? So to be very precise, if you take this Hamiltonian, if you take this action, this is something which is O4 symmetric, and then so you have an O4 symmetric. That means you have a 4-component order parameter. 3 components are spin, and 1 component is the dimer order, right? The dimer mass terms. And if you bias this towards the spin, then that gives you a marginally irrelevant perturbation. If you bias this towards the dimer, this gives you a marginally relevant perturbation. So that gives you a transition from a dimer phase to a spin, right? A Heisenberg chain. And at the critical point, essentially, what comes out is this emergent theory. And so this is the one-dimensional version of DQCP, which I think all the papers on DQCP in 2D, 2 plus 1 dimension are trying to generalize this. This is really, so that's why it's interesting. Okay, and you can do this. Everything is built in. So this Heisenberg model will run. We have a Heisenberg model actually in the spin spirals code, right? That's already there. That's inside. Or you could do that also for the Hubbard model, right? You could do a Hubbard model at half filling 1D and calculate the kinetic energy correlations or the dimer-dimer correlations. And you could, these are all predefined structures in the code, and that will work out rather nicely. Okay, that has already been done. I think Toshihiro at one point, we did that in this paper just to check for fun. It works. So SUN, right? So one thing nice thing about the ALF is that you can just by putting a parameter in front of the action, I don't know if you have seen this or not, but you can start with an SU2 model, and then you put in front of the action, instead of a 2, you put a 4, a 6, an 8, etc., and you go from SU2 to SUN. And when n goes to infinity, you have a saddle point approximation, right? So you can go from mean field to your n equals 2 and see along the way. You can do simulations for each n, maybe not to infinity, I mean, but you know, to a big number. And 20, you know, there are many problems with n, big N, so be careful. And so you can see if the mean field, which we saw this morning, for example, it's a way of saying, is mean field valid? Is there a phase transition between big N and the small n, right? So this is something you can do, and you can play with this, right? You can play with this, so you could do a SUN Hubbard model. This is also pre-programmed, and you can play with the half-filled case if you want, and you'll see that if you take the SU4 Hubbard model in the representation we have here, then you have a dimer phased, right? So you will see that dimer comes in as for n equals 4. For the two-dimensional case, at n equals 4, we still have a magnetically ordered state, and at n equals 6, we have a dimerized phase, right? Can you write the program for the SUN quantum antiferromagnetic in the self-adjoint antisymmetric representation? Yes, I can. Can you try it? Okay. Then here are dynamics. So what we didn't talk at all about max end, right? Correct. So what ALF has built in is also a possibility of doing the analytical continuation from imaginary time to real time. So this is a ill-defined procedure. So it's hard, and you have to be careful when you do it. But nevertheless, you see it does work. This is the case. This is taken from the ALF documentation. And now in the modern version of the ALF documentation, we have two types of maxent. We have classic maxent, it's called, and stochastic maxent. So you can compare things. So this is a one-dimensional Hubbard model, again at half filling, U over T equals 4, beta equals 10, and 46 sites, right? And then you see that, well, it's an interesting phase in the sense that this is the charge. So there's a charge gap. There's nothing up to here, right? There's the charge. You have to pay some energy to do a charge excitation, but there is no spin gap, right? And this is essentially what this would give you some intuition of fractionalization. This would be something like a 2-spin-on continuum. Actually, there are some experiments on potassium copper chloride, where you can really see the experiments which really work with this, right? So this is a pretty, oh, I shouldn't say that, I'm going too far. But anyways, and this is then the single particle spectral function. You see that the single particle spectral function also has a gap, but has a rather complicated structure, which gives you information, if you want, on the fact that in 1D, if you put an electron in your system, it splits into two particles. It splits into a spin-on. That would be the spin-on branch. And if you believe me here, this would be something like a hole-on branch, right? So if you put in a particle, it splits into two excitations which move at different velocities, and so et cetera, right? So this is nice to try the maxent. So everything should work out of the box, but of course there are details to work nicely. Then these are all proposals. We can work on them together, etc. How do I go back? How do I go back? Yeah, thank you. Okay, go back. So topology, churn insulate, churns. So we can do correlation effects in churn bands. So what you can do, I won't go through this, but this would be something like a pi flux lattice. This is a square lattice, a pi flux lattice. So on every one of these lines, every second line, I put a -1. If you want a -1 to the, I change the sign of the hopping, and that means that you have a pi flux going through each plaquette, and that gives you a regularization of the Dirac Hamiltonian with C4 symmetry. And then so you would have this would be the Dirac Hamiltonian, HT would be this, right? It's a unit cell. Because of the pi flux, you have a unit cell of 2, right? Because if I look here, then it's different than here, because you have a minus sign here, I would have a plus sign, no? So there's a unit cell of two atoms. And so this would be my Dirac discretization of my Dirac Hamiltonian. And then here I can put in some mass term. This would be a quantum spin Hall mass term. I won't go through it here, but you can program it. And so that this H Dirac plus HQSH is basically a quantum spin Hall state, right? So it's basically 2 times a Haldane model with a churn +1 for one spin and a churn -1 for the other spin. And then you can add some interactions, right? So you can do many things here which are pretty fun, right? So you can now we can play with the sign of the interaction. And if the U is negative, because you have time reversal symmetry, you will encounter no no sign problem, even if you dope the system. So I could put in the chemical potential, which is not put into here. And then you can start playing with things which Johannes did, some understanding, try to understand, does superconductivity, is the topology of the band, basically, does it affect superconductivity? And I think that was a question. I think your answer is maybe no, right? Some people still say yes.
Well, I mean, there's a bit of a discussion.
There's still some discussion. I didn't follow it. So Johannes.
So,
sorry? Sorry, the box. Here you go. Up.
yeah, so there was a bit of a discussion that you can look at this from a mean field perspective and you find a superfluid stiffness, which can be related to the quantum geometry. And there might be, or there was a proposal for a lower bound on the superfluid stiffness given by the Chern number. So this gave the impression that the topology does play a role. But then again, if you think about the statement that you have a superfluid stiffness, which is finite, this is equivalent to saying that you have a superconductor. But when you work with flat bands, you have to be careful about competing instabilities. So take lower bounds there with a grain of salt. And I think now we understand that this is maybe more related to the actual width of the orbitals. Where
right. Basically how the orbitals are compared to how the topology of the orbitals more than the topology of the band.
Yes,
right?
And if you have a Chern band, you know that the orbital has to have some finite width.
Right.
But if you have a exponentially localized Wannier state, you can still have a finite width. And the finite width was more important than the long tail behavior.
So I think this is really nice because it's something which works out of the box, correct? It's not complicated to do, and it's really interesting physics. So there are many things like this which are maybe still easy catches with the ALF. Then edge physics, we played a lot with this. So this would be an example of what the high energy people would call domain wall fermions, correct? I don't know how they call that. So you would have you have a quantum spin Hall state, so you have a gap in the bulk, and at the edge you have a single Dirac cone, right? And so you can really then look at the correlations effects on a single Dirac cone at the edge. So you're looking for interactions in 1+1 dimension. A single Dirac cone is something with an anomaly, so you can't put it on the lattice, but you can just put it on the edge of a system and just calculate one edge, right? And push the other edge to infinity. So you want to calculate 1+1D, but because of the anomaly, you have to match the anomaly with another edge and then effectively simulate 2+1D. So you can play with this if you want, and then you get very close to the high energy physicists who want to do this for 5D, right? I think that's, I don't know. But so they don't use ALF, right? They use something else. Good. Okay, so these are edge physics. That's all you can do many things here. This is a technical thing which I think we talked about. This is how to change how the choice of the Hubbard-Satonovich transformation affects the autocorrelation times. And so I think that this is an example you take for an attractive Hubbard model. You can take two different Hubbard-Satonovich transformation, ones which couples to the spin, right? To the spin. So U would be negative here, so that would be something which become complex, but there would be no sign problem. We can show that because of time reversal symmetry. And then for the negative U, you would couple to the charge, okay? So it turns out that the charge is a slow mode and the spin is a quick mode. And so if you, for the negative U, and this is a beautiful example where you see that if you take this and you base your Hubbard-Satonovich on this, you get very good autocorrelation times. If you base your Hubbard-Satonovich on this, it's not very good, right? So you can write the code, just change it. It's basically a label you have to change. Look at the autocorrelation time. That's a flag you put into the parameter file. And you see that you will not miss the fact that one code works extremely well and the other very badly. So the moral of this, I mean, what you learn from this is that always try to couple your Hubbard-Satonovich. I mean, this is intuitive. I can't prove it, but always try to couple your Hubbard-Satonovich fields to high energy modes that move quickly. If they couple to low energy modes that are stuck and don't move, you will somehow go into autocorrelation time problems, right? It's not so easy to do, right? Sometimes you don't have the possibility. Here you do have the possibility, so it's a nice example. Okay. Then yeah. So this is work which is done by Emily, and so there is a so you will agree that in classical mechanics, I guess that the Ising model is important. And so now when you do fermions, quantum criticality with fermions, I guess that the easiest possible phase transition with fermions is a Dirac system, right? To charge density wave for spinless fermions, right? So that's what you call a Grosvenor Ising universality. So you can simulate this, and I think it's still, I haven't kept up, but I think that a lot of people are still very unhappy about the exponents, the understanding of the exponents, can we calculate them? Can we compare them to bootstrap? I don't know how far, do you know how far bootstraps are? It's already pretty good. So it's okay. So people are happy, even people like Michael Scherer is happy because he has very high standards. Yes. He's happy now. Okay, so try it. Okay, so for the Ising, and then I guess for the Heisenberg, maybe not, and then for the U1, maybe not. I don't know. But these are you can write down a TV model on the pi flux lattice. This is all built into in the model in the alpha Hamiltonian. You can look at quantum criticality, Grosvenor criticality. Then this is something a body of work which has been done by I think the person to talk about here is Marcin. So Marcin who's here? Where is he? Marcin has been working a lot on Kondo systems, and so Kondo is actually really very nice because this is an old paper, but go and look at Marcin's paper. Who's here? Talk to him. Kondo is really nice because this is a case where we were talking over lunch by this, but because it's really nice because in the ALF you can show, and that's a very nice work of Marcin, is that you can go from large n to n equals 2. That means from the saddle point, which people like Pierce Coleman do all the time, and you can verify that this is the correct saddle point. That means if you go from n infinity to n equals 2 for the heavy fermion state, or Kondo insulating state, which is a special case of a heavy fermion state, then you have no phase transition. So this is also in the ALF. You can just run the Kondo lattice code. And then I have one more that was talked about this morning, I think. This is so spin systems, right? So you can do spin systems, and that comes from how do we do spin systems in ALF? Well, it's it's not written down here, but essentially the way you do spin systems in ALF is you have to fractionalize the spin. So your spin operator here is written as these are abricosal fermions, they're called. So they have no charge, but they actually have a gauge charge, because once you want to include the constraint, you have to include this constraint. This F becomes a sort of you impose this constraint by a gauge, by a local U1 gauge invariance, for example. Okay, so the point is here is that what the ALF does is it takes this and it follows papers by Anderson, Affleck, etc., and transform the Heisenberg model into a QED3 problem. So quantum electrodynamics in 2 + 1 dimensions, or in 1 + 1 dimension, as you want to put it, and it solved this QED3 problem, right? So this is a way so what the ALF does is really do some high energy physics to understand this spin-spin correlations. Of course, most of the time, the gauge field is confined, right? A spin liquid would be the case where it's deconfined. So that could happen, but not all the time. So you can do spin correlations. You can do really QED3, do spin Heisenberg models in the terminology of QED3. And in the last ALF workshop, somebody says, "Hey, I'm interested in Jablonski-Moria." So Jablonski-Moria is something like this: breaks time reversal symmetry. And so these are terms S cross S of J. And my claim is that you can do that in the ALF by saying for spin 1/2 at least, we know how to do this by doing the abricosal fermions, and so that you can look in the code in the documentation how to do this, or you can ask me and I'll explain it to you. And then for the Jablonski-Moria term, you can write this in terms of a perfect squared and try your luck. Here, you won't have a sign problem, provided that you have no frustration. If there's frustration, you'll get a sign problem. This will give you a sign problem, right? And I put up this paper here because it's this amazed me. Maybe I'm the only one who's amazed. But it's this way of doing frustrated spin systems is really good, right? So the claim is that doing this is really good because you can optimize your formulation to get a pretty good sign problem and to go down to pretty low temperatures, which are good for experiments, right? So in this paper, we use these ideas to do Monte Carlo simulations for generalized Kita-F models. And in some later papers, we actually were able to compare experimental data with simulations from the ALF down to 40 Kelvin for realistic models of Kita-F for ruthenium trichloride, and it works, right? So that's pretty impressive. We were very happy about this. And then at the end, I mean, these are suggestions. So we have 10 suggestions. They're all online. And of course, the best thing for you to do is to find your own problem, right? And try to implement it. And we're here till Friday, right? To discuss and to see. Questions? No questions. Questions? I think we're tired. Who's the chairman? Where's the chairman?
He's tired.
He's tired. He gave up. So I'm chairing myself. He's tired. So questions online.
So in the K-Lee-Hubbard problem, if you
Yes.
turn on the sublattice potential, would that also still make the problem side problem free at half filling with positive U?
So somebody read, or did you send me the mail asking me this
Yeah,
question?
yeah, I did.
Listen, I think it does. So the question is, it's repulsive. You want repulsive, of course.
Yes.
Yeah, I understood repulsive, right? Because you were talking about it. So the question is, if for the repulsive, what you want to do is to put a plus chemical potential here and a minus chemical potential here, correct?
Right.
So I think that it will put in a you see, you're correct. You don't wait. It doesn't break particle hole symmetry, but it breaks the partial particle hole symmetry you need, right? So I think that it will mess it up. But I'm reading your mail. I was trying to do. I still don't have I think it will, but I'm not sure. So maybe you can try.
Yeah, I will do this project.
Yeah, do this project and put in the chemical potential of it. That's very easy to put in. And then don't use any predefined structure. Just program this right away. It's much easier.
Okay.
Okay, then we can talk about it and see. But my claim is that it may put in a sign problem. That's my feeling, but I'm not sure. Okay.
Okay.
Yeah, that's what I believe. But I have to do the calculation. Yeah. So this is one project. Okay. No, because the symmetry is broken at the Hubbard-Satonovich field. I think so. I don't think it will. I don't know. Okay. So this year tomorrow we sort of have a lot of talks, right? So there's not as much time, but we still have time now, and we have time tomorrow afternoon. And then on Friday there will be some presentations of or discussions / presentations of what you tried to do, even if it worked or did not work. Okay. Good. So thank you.